On August 30th, 2019, the Asteroid Terrestrial Impact Last Alert System telescope in Hawaii captures something moving against the star field. The object appears as a faint smudge of light, unremarkable at first glance, yet its trajectory marks it as extraordinary. It moves too fast and at too steep an angle to belong to our solar system's family of planets, asteroids and comets. The designation comes quickly, 3I/Atlas, the third interstellar object ever detected passing through our cosmic neighbourhood. Only the patient mathematics of orbital mechanics reveal the profound strangeness of this visitor. Its hyperbolic path carries it not from the outer reaches of our own solar system, but from the vast darkness between stars, somewhere in the galaxy's spiral arms. Perhaps decades or centuries ago, this fragment began a journey that would bring it sweeping past our sun at more than 40 kilometers per second. The speed alone whispers of origins far beyond the gravitational embrace that holds our planets in their familiar dance. In the weeks following discovery, astronomers train their instruments on this wandering piece of the galaxy. The light it reflects carries signatures that speak of composition and history, of processes that shaped it long before Earth drew its first breath. Unlike the rocky asteroids born in our solar system's violent youth, or the icy comets that formed in its distant reaches, 3I/Atlas presents a puzzle written in wavelengths of scattered sunlight. The object's behaviour near the sun offers another mystery wrapped in gentle paradox. As it approaches our star, it begins to brighten and develop what appears to be a faint coma, the hazy envelope of gas and dust that typically marks a comet awakening to solar warmth. Yet its spectrum reveals none of the water ice or frozen carbon dioxide that drives such transformations in objects native to our solar system. Whatever volatile materials sublimate from its surface remain largely unidentified, their chemical signatures foreign to the familiar inventory of our planetary neighbourhood. Spectroscopic measurements hint at a composition rich in heavy elements, the metals forged in stellar cores and scattered by stellar death. Iron, nickel, and traces of elements that require the intense pressures and temperatures found only in the hearts of dying stars. These are not the pristine materials from which our solar system condensed 4.5 billion years ago, but rather the processed remnants of nuclear furnaces that burned and died long before our sun ignited. The visiting fragment measures perhaps a few hundred meters across, small enough to fit comfortably within a terrestrial valley, yet it carries within its rocky matrix the compressed history of stellar evolution. Each atom of its substance speaks of fusion reactions that lasted millions of years, of the patient conversion of hydrogen to helium to carbon to oxygen, climbing the periodic table through successive burning phases until the star's core could no longer sustain itself against its own weight. Astronomers calculate backward along its trajectory, tracing the object's path through space and time. The mathematics suggest a journey lasting hundreds of thousands of years, during which 3I/Atlas drifted through regions of space where starlight arrives as faint whispers and the cosmic background radiation provides the only warmth. In this interstellar winter, temperatures hover just a few degrees above absolute zero, cold enough to freeze any atmosphere into frost that clings to rocky surfaces like ancient memory. The silence of this journey defies earthly comprehension. No weather stirs its surface. No erosion carves new features into its contours. Only the patient bombardment of cosmic rays and the occasional impact of microscopic dust grains mark the passage of millennia. It tumbles slowly through the vacuum, its rotation a legacy of whatever catastrophic event first sent it wandering between the stars. What violence could accelerate a fragment of rock and metal to such speeds that it escapes not merely a planet's gravity, but the gravitational embrace of an entire star system? The energy required suggests events that dwarf even the largest impacts recorded in our solar system's turbulent youth. Planetary collisions, the tidal disruption of worlds by dying stars, or the explosive ejection of material during stellar collapse, processes that operate on scales where the destruction of entire worlds becomes merely a footnote in cosmic evolution. The fragment's arrival in our solar system represents a moment of rare intersection between two vastly different histories. For billions of years, our sun has maintained the stable nuclear burning that keeps Earth warm and permits the patient evolution of life. Meanwhile, 3I/Atlas carries the signature of stellar death, of fusion reactions that burn too hot and too fast, consuming their fuel until only collapse remained. As it passes closest to our sun, the interstellar visitor begins to reveal more of its secrets. Solar radiation heats its surface for the first time in perhaps millions of years, causing sublimation of materials that have remained frozen since its ejection from whatever system gave it birth. The gases that stream away form a tenuous tail, visible to sensitive instruments as a faint brush stroke against the darkness. Yet even this moment of revelation carries profound mystery. The composition of the outgassing suggests materials formed under conditions unlike those in our solar system's birth nebula. Isotope ratios speak of nuclear synthesis in stellar cores different from our sun, of chemical processing in environments where different abundances of heavy elements influence planetary formation. This wandering fragment serves as an involuntary messenger from stellar systems that evolved under different circumstances, perhaps in regions of the galaxy where star formation proceeded with different rhythms and different outcomes. The object's brief passage through our solar system, lasting mere months, represents only the smallest fraction of its cosmic journey. Soon it will return to the interstellar depths, carrying its ancient secrets back into the space between stars. Its visit offers humanity a glimpse of processes that shape the galaxy on scales far beyond our direct experience. A reminder that the universe contains multitudes of stories written in languages of physics and chemistry that we're only beginning to learn to read. The peculiar dance of 3I/Atlas as it approaches our sun defies the familiar choreography of solar system objects. Comets from the Oort cloud follow predictable patterns as solar radiation awakens their frozen surfaces, water ice sublimating first, followed by carbon dioxide and other volatiles in a sequence determined by their respective vapor pressures. The resulting coma expands in characteristic ways, forming the classic teardrop shape as solar wind carries away the liberated gases. Yet 3I/Atlas performs a different dance entirely, one that speaks of origins in stellar graveyards rather than the pristine nurseries where planets are born. As the object draws closer to our star, instruments detect the beginning of outgassing at distances where water ice should remain stable. The spectral signatures reveal materials that have no place in the familiar inventory of solar system volatiles. Carbon-bearing compounds with molecular structures suggesting formation under extreme pressures and temperatures. Silicon-rich particles that may have condensed from stellar atmospheres during the violent final stages of stellar evolution. Traces of noble gases with isotope ratios that point to nuclear processes fundamentally different from those that enriched our solar nebula. The brightness curve of 3I/Atlas as it approaches perihelion follows no known pattern. Traditional comets brighten according to well-established relationships between distance from the sun and the sublimation rates of their constituent ices. The mathematical relationships that govern these transformations have been refined through centuries of observation, allowing astronomers to predict comet behavior with considerable accuracy. Yet 3I/Atlas brightens in fits and starts, its luminosity fluctuating in ways that suggest a complex interplay between solar heating and surface composition. Detailed photometric observations reveal that different regions of the object respond differently to solar radiation. Some areas begin outgassing while others remain inert, creating an asymmetric coma that evolves in unexpected directions. The pattern suggests a surface composed of distinct materials with different volatile content, perhaps fragments from multiple sources welded together by some ancient catastrophic event, like a geological breccia formed by impact, but operating on scales where entire worlds serve as the raw materials for construction. The rotation period of 3 was /Atlas, measured through careful monitoring of its brightness variations, reveals another layer of complexity. The object tumbles through space with a period that varies slightly over time, suggesting either a complex internal structure or the preferential outgassing of materials from specific regions of its surface. This variable rotation speaks of a body that has been shaped by processes unlike the gradual accretion that formed most objects in our solar system. Spectroscopic analysis during the object's closest approach to the Sun reveals absorption lines that have puzzled astronomers since the first measurements. The spectrum shows evidence of crystalline minerals that form only under conditions of extreme temperature and pressure, conditions more consistent with the cores of disrupted planets than with the cold outer reaches of stellar systems where comets typically originate. Olivine and pyroxene with crystal structures suggesting formation at depths of hundreds of kilometers below planetary surfaces, subsequently exposed and ejected during some unimaginably violent event. The mystery deepens when astronomers attempt to model the object's thermal properties. As 3I/Atlas absorbs solar radiation, it should heat according to well-understood principles of radiative transfer. Yet infrared observations reveal temperature distributions that suggest unusual thermal conductivity properties. Some regions of the surface heat and cool more rapidly than expected, while others maintain surprisingly stable temperatures despite changing solar illumination. The pattern hints at internal structure with voids or cavities that insulate different portions of the object from thermal variations. Radio observations add another dimension to the puzzle. As solar radiation heats the surface of 3I/Atlas, some of the outgassing materials become ionized, creating a weak but detectable radio signature. The frequency and intensity of these emissions provide clues about the magnetic environment around the object and the nature of the particles being released. Unlike the relatively simple radio signatures of solar system comets, 3I/Atlas generates complex patterns that vary with its rotation and distance from the Sun. The chemical composition revealed through spectroscopy tells a story of processing under conditions that existed nowhere in our solar system's formation. Heavy elements appear in abundances that speak of multiple generations of stellar nuclear synthesis. Elements like nickel, cobalt, and chromium show isotope ratios consistent with formation in the cores of massive stars, stars that lived fast, burned bright, and died in supernova explosions that scattered their processed material across vast regions of space. Perhaps most intriguingly, trace amounts of elements heavier than iron appear in the spectrum, elements that can only be formed through the rapid neutron capture processes that occur during the most violent stellar explosions. These R-process elements serve as signatures of stellar death, markers of events so energetic that they briefly recreate conditions that existed only in the first moments after the Big Bang. Their presence in 3I/Atlas suggests origins not merely in stellar destruction, but in the most extreme forms of stellar death. The object's trajectory through our solar system provides additional clues about its origins. Unlike objects native to our stellar neighborhood, 3I/Atlas approaches from a direction that when traced backward through galactic motion, points toward regions of space where stellar formation rates have been historically high. Dense clusters where massive stars burn through their nuclear fuel in mere millions of years before ending their lives in spectacular explosions that enrich the interstellar medium with heavy elements. As 3I/Atlas continues its journey toward perihelion, ground-based telescopes and space-based instruments maintain their vigilant watch. Each measurement adds another piece to a puzzle that challenges conventional understanding of how objects move between stellar systems. The energies required to accelerate even a small fragment to interstellar velocities point to processes that operate on scales where the destruction of entire planetary systems becomes merely a side effect of stellar evolution. The visitor's brief presence in our solar system offers a rare opportunity to study material processed by stellar evolution in environments unlike those that shaped our own world. Every photon of reflected sunlight carries information about nuclear processes that occurred in stellar cores millions or billions of years ago. Every molecule released during outgassing represents a sample of chemistry that took place under conditions of temperature and pressure that Earth has never experienced. Yet for all the measurements and analysis, 3I/Atlas remains fundamentally alien to our solar system's family of objects. Its composition, behavior and trajectory all speak of origins in stellar environments that follow different evolutionary paths. It serves as a messenger from regions of the galaxy where different conditions prevailed during planetary formation, where different abundances of elements influence the chemical processes that build worlds. The object's gradual approach to the Sun represents a moment of convergence between two vastly different histories. Our solar system's 4.5 billion year story of stable stellar burning and gradual planetary evolution, and the fragment's own history of violent stellar death and interstellar wandering. For a few brief months, these histories intersect as 3I/Atlas passes through our cosmic neighborhood before returning to the vast emptiness between the stars. The galaxy operates as a vast recycling system, where stellar death serves as the primary mechanism for distributing heavy elements throughout the cosmic web. When massive stars reach the end of their nuclear burning phases, they do not simply fade into darkness like candles guttering out. Instead, they undergo catastrophic collapse followed by explosive resurrection, scattering their processed cores across distances measured in light years. This stellar archaeology operates on timescales that dwarf human comprehension, yet it provides the essential foundation for all complex chemistry in the universe. The most massive stars burn through their nuclear fuel with reckless intensity, converting hydrogen to helium, helium to carbon, carbon to oxygen, in a sequence of fusion reactions that climb steadily up the periodic table. Each burning phase generates elements heavier than those produced in the previous stage, but also burns hotter and faster, consuming fuel at exponentially increasing rates. A star that might burn hydrogen for 10 million years will exhaust its carbon fuel in mere centuries, its oxygen in months, its silicon in days. The final burning phase, which produces iron in the stellar core, lasts only hours before the nuclear fires can no longer sustain themselves against gravitational collapse. When the core can no longer generate sufficient energy to support the star's enormous mass, collapse occurs with breathtaking swiftness. The core, composed primarily of iron nuclei and electrons, contracts from a volume larger than Earth to a sphere barely 20 kilometers across in less than a second. The gravitational energy released during this collapse exceeds the total energy output of our Sun over its entire 10 billion year lifetime, concentrated into a moment briefer than a human heartbeat. The shockwave generated by this collapse rebounds from the impossibly dense core, and races outward through the star's outer layers at velocities approaching 30,000 kilometers per second. As it travels, the shockwave encounters successive shells of nuclear-burning products: silicon, oxygen, carbon, helium, each representing a different epoch in the star's evolution. The passage of this shock front through these layers creates conditions even more extreme than those in the original stellar core, triggering explosive nuclear synthesis that produces elements far beyond iron on the periodic table. In the space of minutes, a single supernova explosion manufactures more heavy elements than our Sun will produce during its entire existence: gold, platinum, uranium, elements that require the rapid capture of neutrons under conditions of unimaginable density and temperature. These R-process elements can form nowhere else in the universe, making every supernova a cosmic mint that produces the raw materials for future generations of stars and planets. The explosion that destroys the parent star also serves as the delivery system for these newly minted elements. Material accelerated to velocities of thousands of kilometers per second streams away from the explosion site, forming an expanding bubble of superhot gas that will continue growing for hundreds of thousands of years. This supernova remnant carries the stellar ashes far from their point of origin, mixing them with the tenuous interstellar medium and enriching vast volumes of space with heavy elements. Yet not all material from dying stars travels in the form of diffuse gas. The most violent phases of stellar evolution can accelerate solid fragments to velocities sufficient for escape not merely from the parent star, but from its entire gravitational sphere of influence. Planetary debris, asteroid-sized chunks of stellar core material, and fragments of partially disrupted companion objects can all achieve interstellar velocities during these catastrophic events. The process operates with a casual efficiency that belies its tremendous violence. A star that has spent millions of years carefully crafting heavy elements in its core disperses this precious cargo across hundreds of cubic light-years in the space of a few thousand years. The expanding shock front sweeps up existing interstellar material, compressing and heating it until new generations of stars begin to form from the enriched mixture. These stellar nurseries inherit not only the hydrogen and helium from the Big Bang, but also the full inventory of heavy elements produced by previous generations of stellar evolution. This cosmic recycling operates with patience measured in galactic rotation periods. Material ejected from a supernova may drift through interstellar space for hundreds of millions of years before encountering conditions suitable for incorporation into a new stellar system. During this extended journey, the fragments experience an environment fundamentally different from any planetary surface. Temperatures hover just a few degrees above absolute zero, while cosmic radiation slowly alters their chemical and physical properties. The interstellar medium through which these fragments travel is itself far from empty. Sparse clouds of gas and dust, the remnants of previous stellar deaths, provide occasional encounters that can alter trajectories and modify surface compositions. Magnetic fields threading through space deflect charged particles and create complex patterns of cosmic ray exposure. Over millions of years, these influences gradually transform the wandering fragments, erasing some signatures of their origins while creating new ones. Gravitational encounters with massive objects, other stars, dense molecular clouds, or even black holes can dramatically alter the paths of interstellar wanderers. A close approach to a stellar system might accelerate a fragment to even higher velocities, or conversely, capture it into a new orbital family. These gravitational slingshot effects operate with the same mathematical precision that governs spacecraft trajectories, but on scales where the target destinations are measured in parsecs rather than astronomical units. The most energetic stellar explosions, those involving the most massive stars or occurring in binary systems where material can be concentrated before ignition, generate fragments with velocities approaching significant fractions of the speed of light. These hypervelocity ejecta carry such enormous kinetic energy that they can escape not merely their parent star system, but even the gravitational well of their host galaxy, like seeds scattered on cosmic winds. They carry the chemical signatures of stellar death into the vast spaces between galaxies. The composition of these stellar fragments reflects the specific nuclear history of their parent stars. Elements produced during different burning phases retain characteristic isotope ratios that serve as fingerprints of the conditions under which they formed. Silicon bearing the signatures of oxygen burning, iron with neutron-to-proton ratios that speak of the exact temperature and density conditions in collapsing stellar cores, trace elements that reveal whether the parent star evolved in isolation or as part of a binary system where material could be exchanged between stellar companions. Modern stellar archaeology has revealed that our solar system itself bears the chemical signatures of multiple previous generations of stellar death. The heavy elements incorporated into Earth's rocky layers tell stories of supernovae that occurred billions of years ago, their shrapnel eventually finding its way into the molecular cloud from which our sun and planets condensed. Every atom of carbon in human bodies, every nucleus of oxygen we breathe, every grain of silicon in terrestrial rocks represents processed stellar material, recycled through the cosmic ecosystem and incorporated into new forms. Yet while our solar system formed from well-mixed material that had been processed through multiple cycles of stellar birth and death, objects like 3/8 may carry more direct signatures of individual stellar catastrophes, rather than the average chemical composition that characterizes objects formed in stellar nurseries. Interstellar fragments can preserve the specific isotope ratios and elemental abundances of single, identifiable supernova events. The study of these cosmic messengers provides a unique window into stellar evolution processes that occurred at specific times and places in galactic history. Unlike the diffuse gas clouds that have been thoroughly mixed by turbulence and magnetic fields, solid fragments maintain their chemical integrity across vast distances and cosmic time periods. They serve as time capsules, preserving samples of stellar cores and planetary debris from epochs when the galaxy was younger and stellar formation proceeded under different conditions. As telescopes become more sensitive and analytical techniques more sophisticated, astronomers expect to identify increasing numbers of these interstellar visitors. Each one carries a unique story written in atomic nuclei and crystalline structures, tales of stellar systems that evolved along different paths and met different fates. Together they provide an expanding library of galactic history, samples of stellar archaeology that extend our understanding of cosmic evolution far beyond the boundaries of our own solar system. The light reflected from 3/Atlas carries within its wavelengths a chemical autobiography written in the language of atomic absorption and emission. When astronomers spread this faint starlight into its component colors, using high-resolution spectrographs, they reveal a barcode of dark lines where specific elements have absorbed particular frequencies of electromagnetic radiation. Each line corresponds to electronic transitions within atoms, signatures as unique and identifiable as human fingerprints. Yet the pattern displayed by this interstellar visitor differs markedly from the familiar spectra of objects native to our solar system. The most striking differences appear in the isotope ratios of common elements. Isotopes are variants of the same element that contain different numbers of neutrons in their atomic nuclei. While they share identical chemical properties, isotopes form under different nuclear conditions and serve as markers of the specific environments where stellar nuclear synthesis occurred. The oxygen isotopes detected in 3I/Atlas, for instance, show ratios that point to formation in stellar cores with different mass, temperature, and burning duration than those that enriched our solar nebula. Silicon, one of the most abundant rock-forming elements, appears in the spectrum of 3I/Atlas with isotope ratios characteristic of explosive nuclear synthesis. During the final moments of stellar collapse, silicon nuclei undergo rapid transformation in environments where temperatures exceed 5 billion degrees and densities approach that of atomic nuclei themselves. These extreme conditions favor different nuclear reaction pathways than the relatively sedate processes that occur during normal stellar burning, producing silicon isotopes in proportions that serve as unmistakable signatures of stellar death. The presence of rare Earth elements in the fragment spectrum provides additional evidence for exotic origins. Elements like europium, gadolinium, and dysprosium can only be produced through slow neutron capture processes that occur in the extended atmospheres of certain types of evolved stars. These S-process elements form when atomic nuclei have sufficient time to capture neutrons and undergo radioactive decay before encountering additional neutrons. The specific abundances detected in 3I/Atlas suggest formation in stellar environments with neutron flux densities that differed significantly from those in our solar system's formation region. Perhaps most telling are the traces of technetium detected in the object's spectrum. Technetium occupies a unique position on the periodic table as the lightest element with no stable isotopes. All technetium isotopes undergo radioactive decay with half-lives measured in millions of years or less. The presence of detectable quantities of this element in 3I/Atlas therefore provides a direct constraint on the timeline of its formation and ejection from its parent system. The technetium must have been produced relatively recently in galactic terms, within the last few million years, or it would have decayed beyond detectability. The crystalline structure of minerals within the fragment, inferred from the polarization properties of reflected light, reveals additional clues about formation conditions. Certain crystal structures can only form under specific combinations of temperature, pressure, and chemical environment. The olivine crystals detected in 3I/Atlas show lattice parameters consistent with formation at pressures exceeding those found in Earth's mantle, suggesting origins deep within a planetary body that subsequently experienced catastrophic disruption. Magnetic field measurements conducted as 3I/Atlas passes through our solar system reveal yet another layer of complexity. Many meteorites and asteroids retain weak magnetic signatures acquired during their formation. When they cooled in the presence of magnetic fields generated by their parent bodies, the magnetic properties of 3I/Atlas indicate exposure to field strengths much higher than those typical of planetary formation environments, more consistent with the intense magnetic fields that exist near neutron stars or in the immediate aftermath of supernova explosions. The surface composition of the fragment, analyzed through infrared spectroscopy as solar heating causes sublimation of volatile materials, reveals compounds that have no terrestrial analogues. Complex carbon-bearing molecules with structures suggesting formation under reducing conditions in hydrogen-rich environments. These compounds may have condensed directly from stellar atmospheres during the late stages of stellar evolution, when convective processes bring nuclear burning products to the stellar surface and mass loss carries them into interstellar space. Trace amounts of noble gases trapped within the fragment's crystal lattice provide additional evidence for exotic processing. The isotope ratios of helium, neon, and argon show patterns characteristic of spallation reactions caused by high-energy cosmic ray bombardment over extended periods. Yet the specific ratios suggest exposure to cosmic ray environments different from those encountered in our local galactic neighborhood. pointing to origins in regions of space where stellar density and supernova frequency create elevated backgrounds of energetic particles. The deuterium content of any hydrogen-bearing compounds detected in 3I/Atlas offers clues about the chemical conditions during its formation. Deuterium, the heavy isotope of hydrogen containing one neutron in addition to the usual single proton, is destroyed by nuclear reactions at relatively low temperatures. Its abundance therefore serves as a thermometer for the maximum temperatures experienced during chemical processing. The deuterium ratios in 3I/Atlas appear depleted relative to interstellar values, suggesting formation or processing in environments hot enough to drive deuterium burning reactions. X-ray fluorescence spectroscopy, conducted using solar X-rays as a probe during the object's closest approach to the Sun, reveals the presence of elements that exist in only trace quantities in solar system materials. Platinum group metals appear in abundances much higher than their typical cosmic ratios, suggesting concentration mechanisms that operate during stellar core collapse or neutron star formation. These elements, essential for many industrial applications on Earth, exist in such low abundances in terrestrial materials that their detection in significant quantities in 3I/Atlas points to formation processes fundamentally different from those that shaped our planetary system. The gamma-ray signature of 3I/Atlas, barely detectable above background radiation, provides evidence for the presence of long-lived radioactive isotopes. Elements like aluminum-26 and iron-60 produced during supernova explosions decay with half-lives of hundreds of thousands to millions of years while emitting characteristic gamma rays. The detection of these isotopes not only confirms recent formation in a stellar explosion, but also provides constraints on the timeline between formation and arrival in our solar system. Perhaps most mysteriously, the spectrum reveals absorption features that cannot be definitively identified with known compounds or crystal structures. These unassigned lines may represent materials that formed under conditions of pressure, temperature, or chemical environment that do not exist anywhere in our solar system. Like Rosetta Stones written in the language of atomic physics, they hint at chemical processes that occurred during stellar evolution in environments that we can observe only through their fragmentary remains. The totality of spectroscopic evidence paints a picture of 3I/Atlas as a composite object, assembled from materials that originated in multiple stellar processing events. Some components may have formed during the quiet nuclear burning phases of stellar evolution, while others bear the signatures of violent explosive nuclear synthesis. Still other materials may have been processed during close encounters with neutron stars or white dwarf companions, where tidal forces and intense radiation fields create exotic chemical environments. As the fragment continues its passage through our solar system, every additional spectroscopic measurement adds new details to this chemical biography. The story that emerges is one of cosmic recycling operating on scales both vast and violent, where the death throes of stars become the birth announcements of new chemical complexity. In the fading light reflected from this small wanderer, astronomers read the signatures of stellar furnaces that burned and died long before our sun ignited, their ashes now carrying messages across the galaxy's spiral arms. When stars like our sun approach the final chapters of their nuclear lives, they undergo transformations that seem almost gentle compared to the explosive deaths of their more massive cousins. Yet this apparent serenity masks processes of extraordinary violence that can completely obliterate any planetary systems that once orbited these dying stars. The death of a solar mass star unfolds over millions of years, but its climactic moments reshape entire stellar neighborhoods and scatter planetary debris across interstellar distances with the casual, inexorable efficiency The transformation begins as the star exhausts the hydrogen fuel in its core after roughly 10 billion years of steady nuclear burning. Without the outward pressure generated by fusion reactions, the core begins to contract under its own gravity, heating until it becomes hot enough to ignite helium burning in a shell surrounding the now inert hydrogen-depleted center. This helium burning proceeds through the triple alpha process, where 3 helium nuclei combine to form carbon, but the process operates with an instability that sends pulses of energy through the star's outer layers, causing them to expand dramatically. As the star swells into a red giant, its surface cools and dims while its radius increases by factors of hundreds. A star that once resembled our Sun grows large enough to engulf the orbits of any inner planets, its tenuous outer atmosphere extending across astronomical units of space. The gravitational effects of this expansion are profound and irreversible. Planets that once maintained stable circular orbits find themselves spiraling inward through increasingly dense stellar material, their orbital energy dissipated through atmospheric drag until they disappear entirely into the star's bloated envelope. The stellar wind during the red giant phase carries away substantial fractions of the star's original mass, sometimes exceeding the mass loss rates observed in the most active solar storms by factors of millions. This wind, enriched with carbon and other products of nuclear burning, streams away from the star at velocities of tens of kilometers per second, carrying enough material to build dozens of Earth-mass planets. Any remaining planets in the outer regions of the system experience dramatic orbital evolution as the star's gravitational grip weakens with each gram of material lost to space. The helium-burning phase proceeds through a series of thermal pulses, each one more violent than the last. During these pulses, convective zones develop within the star that transport nuclear burning products from the core to the surface, creating abundance patterns unlike anything observed in main-sequence stars. Elements like carbon, oxygen, and fluorine, normally locked away in stellar interiors, appear in the star's atmosphere and are subsequently carried away by the intensifying stellar wind. After several million years of this pulsating behavior, the star exhausts its helium fuel and begins the final contraction that will transform it into a white dwarf. The outer layers, no longer supported by nuclear burning, are ejected in a spectacular planetary nebula that expands away from the central star at velocities approaching 100 kilometers per second. This expanding shell of gas, illuminated by ultraviolet radiation from the hot white dwarf core, creates some of the most beautiful structures visible to telescopes, yet represents the complete destruction of whatever planetary system may have existed. The white dwarf that remains after this ejection contains roughly 60% of the original star's mass, compressed into a volume smaller than Earth. Its surface temperature exceeds 100,000 degrees, hot enough that its ultraviolet radiation ionizes the expanding nebula material and drives additional mass loss through radiation pressure. The gravitational field at the white dwarf's surface is so intense that any solid material falling onto it would impact at velocities exceeding 5,000 kilometers per second, releasing energy equivalent to hundreds of nuclear weapons per kilogram of material. Yet the story of planetary destruction extends far beyond the simple engulfment or ejection of orbiting worlds. The asymmetric mass loss during the red giant and planetary nebula phases creates gravitational perturbations that can destabilize planetary orbits even at large distances from the dying star. Computer simulations reveal that the changing gravitational potential can scatter planets into highly eccentric orbits, send them careening into interstellar space, or cause catastrophic collisions between worlds that had maintained stable configurations for billions of years. The most dramatic planetary disruptions occur in binary star systems, where the death of one component creates gravitational chaos that affects the entire system. As one star expands into a red giant, it may overflow its Roche lobe and begin transferring material to its companion. This mass transfer can trigger nova explosions on the recipient star's surface, each one capable of stripping atmospheres from nearby planets or heating their surfaces to temperatures that vaporize rock. The orbital decay of the binary system during this phase can bring the two stars close enough that tidal forces completely disrupt any remaining planetary bodies. When the mass transfer process eventually leads to a thermonuclear explosion on the white dwarf's surface, the violence can accelerate planetary debris to velocities approaching the escape speed from the entire binary system. Type A supernovae, caused by white dwarfs that accrete enough material to exceed the Chandrasekhar limit, can completely obliterate both stars and any associated planets, creating expanding shock waves that carry stellar and planetary debris across vast distances at velocities exceeding 10,000 kilometers per second. The tidal disruption of planets around white dwarf stars creates signatures that astronomers can observe through careful analysis of the white dwarf spectrum. Heavy elements like silicon, magnesium, and iron appear in the atmospheres of many white dwarfs, despite the fact that these elements should sink below the photosphere within thousands of years due to the star's intense gravity. The presence of these pollution signatures indicates ongoing accretion of rocky material, most likely from the disrupted remnants of planetary systems. Detailed studies of polluted white dwarf atmospheres reveal that the accreted material often shows abundance patterns consistent with rocky planets similar to Earth, Mars, or Venus. The ratios of silicon to magnesium, the presence of trace elements like lithium and beryllium, and the overall heavy element content all point to accretion of planetary debris rather than pristine interstellar material. These observations provide direct evidence that planetary system destruction around dying stars is not merely a theoretical possibility, but a common occurrence throughout the galaxy. The timescales involved in these disruption processes ensure that fragments ejected during white dwarf formation have had ample time to cross vast interstellar distances. A planet disrupted around a star that died 500 million years ago could have travelled dozens of light years, carrying its chemical signatures into stellar neighbourhoods that formed under entirely different conditions. The isotope ratios preserved in such fragments would reflect the specific nuclear history of their parent star, creating a library of stellar archaeology scattered throughout the galaxy. Gravitational interactions during the planetary disruption phase can impart enormous velocities to relatively small fragments. While the bulk of planetary material may remain gravitationally bound to the white dwarf or be ejected at modest speeds, a small fraction of debris can achieve velocities sufficient for interstellar travel through gravitational slingshot effects. These hypervelocity fragments carry the most direct samples of exoplanetary material, preserving not only the chemical signatures of their formation, but also the specific conditions that existed during their violent ejection. The magnetic fields that thread through white dwarf systems can accelerate charged particles to relativistic velocities, creating intense radiation environments that further process any surviving planetary material. This radiation can alter the crystal structure of minerals, create new chemical compounds through radiolysis, and implant foreign nuclei into crystal lattices through nuclear reactions. The result is material that bears the unmistakable signatures of having survived passage through one of the most extreme environments in the universe. Recent observations have revealed that some white dwarf systems show evidence for ongoing planetary formation even after the destruction of the original planetary system. Debris disks around white dwarfs, presumably composed of disrupted planetary material, show signs of gravitational shepherding that could lead to the formation of new asteroid-sized bodies. These second-generation objects would have compositions unlike anything formed during normal planetary accretion, incorporating processed stellar material and exotic isotope ratios inherited from the parent star's nuclear burning history. As white dwarfs cool over billions of years, they provide stable gravitational environments where scattered planetary debris can eventually reaggregate into new configurations. The extremely long cooling timescales ensure that these systems remain dynamically active for periods comparable to the current age of the universe. Material ejected during the initial planetary system destruction can return after complex orbital evolution, creating accretion events separated by millions or billions of years